Good morning, everybody. Um, Welcome back from the weekend. Tomorrow's lab is going to be more static stuff. There will be time to work on homework, but I have some exercises that will hopefully help you kind of really dial in all of this statics and these torques, right? And trying to apply the axes. So look forward to that. We are in the last kind of two chapters here, aren't we? The I don't know, the temptation here is to just kind of let it ride, right? Right. But you got to finish strong, right? Finish strong. This is an opportunity, unlike sort of the last two units, to really recover some grades and that sort of stuff. So finish strong, and you'll be okay. I kind of think that this chapter that we're about to do is what everybody thinks physics is. Right? You come in, we do this nifty bait and switch about how cool the universe is, and then we talk about penguins and ladders and things like that, right? And in a lot of ways it is. This is one of my favorite topics because it's not just gravitational force. We've been dealing with gravity the whole semester, haven't we? Like we've talked about the weight of objects, we talked about this force, but we actually haven't talked about like where it comes from and how it functions in detail, all that sort of stuff. And we're finally getting to it, right? It only took 13 chapters and 14 weeks to do it. If physics is anything, it's an attempt to really simplify our explanations about how the universe works. And I know that sounds weird because of all the complexity, right, that we've had to go through this semester. But physicists, what we're trying to do is explain how everything in the universe works with as few ideas as possible. And it really is kind of astounding that we can describe how balls can fly through the air, or penguins can slide down ramps, or how ladders work with this toolbox that consists of a few forces, some energy, right? And then, of course, a whole bunch of math to try and describe it. In physics, we have four fundamental forces that exist that we can use to describe every observation and every interaction we see in nature. And I know you've heard of several of these forces already, but we'll just kind of lay them all out here. And it seems kind of weird that we really have spent an entire semester and just gotten to the first of the fundamental forces, which is gravity. The second you won't learn about till physics 4b, which is the electromagnetic force. Electricity and magnetism sort of come together in one cohesive form in that semester. So we have gravity, we have electromagnetism, and then forces 3 and 4 you'll get, if you take 4c, you'll get in physics 4c. And those are the strong nuclear force, the force that basically holds every atom together in the universe, and then the weak nuclear force, which is responsible for radioactivity. So with either one or a combination of those four fundamental forces, we can describe everything that happens in the universe. That is pretty audacious, astounding, and amazing, right? If you kind of think about it, that we as a species have come from, ooh, look, we can make fire, to, ooh, look, we can bang rocks together, to, ooh, look, we can put rockets into space. I know there was a lot of in between there, right? But that's the idea. How do I introduce this profound topic, right? I love the spaceship that we're on, right? It's the only spaceship we've got so far that can really sustain us and take us places. And before we dive into sort of all the nitty-gritties of gravity and things like that, I do want you to kind of I want to set the mood, right? if there's one thing that really, I think, distinguishes us as a species and race apart from the other animals and plants and everything that's out there, humans seem to have an inbuilt desire to figure out what's on the other side of the horizon. We need to know what's on the other side of the trees. We need to know what's on the other side of the mountain. We need to know what happens when you keep sailing, right, over the edge of the planet, so to speak. And I don't think that that's changed, because the new horizon that we seem to be pushing towards is the horizon of space, right? Not that we have discovered everything here on our beautiful planet. There's plenty more to discover, especially in the oceans. But we, as a species, have this drive to keep going and to keep discovering and to keep exploring, right? And so what we're going to do today is catch just like a glimpse or a glimmer of how that works, how we can actually achieve getting off of our planet and really start exploring and colonizing our solar system and beyond. And so I need you to just kind of buckle up, right, and get ready, because this is rocket science, right? That's where this is going, okay? Gravity is an amazing thing. And this is a picture, it's a Hubble Space Telescope picture of 3 galaxies that are all in the process of merging. They're, quote unquote, colliding with each other. They're not going to touch each other because the scale of this is amazing and the distance between stars is absolutely incredible. Just to give you sort of an insight as to how big this is, okay? Do you see this kind of wispy blue arm that's sort of extending off to the left, the right-hand side of the picture here? Okay. So our entire galaxy can fit inside of that blue wispy thing. Okay. And our galaxy is about 100,000 light years across. It takes light 100,000 years to go across our galaxy. Our galaxy can fit in that one thing, right? So the scale here is absolutely incredible. But even at this scale, the gravitational forces that are pulling, right, these 3 objects together exist. And the gravity can come down from that scale to the scale of our planet to the scale of my keys, right? Falling to the, like, there seems to be, right, an infinite range of scale here that is really, really hard to appreciate. And so Newton, and we're going to talk more about Newton today. Newton is credited with, I don't like this word, discovering gravity. Did Newton discover gravity? No. Okay, he did not discover. I think gravity was discovered when the first of our ancestors came down out of the trees and said, hey, I think walking's a kind of a fun idea, and then proceeded to trip. I think tripping was the first thing that happened, right? Not walking. And so why is Newton associated with this, and what did he discover that was so incredible? Because inasmuch as Newton was a jerk, and I don't like him at all, there was something genius to the idea that I'm about to express to you, okay? So, I don't know if I quoted this to you before. Alexander Pope, any of you that paid attention in your English classes or your classics classes had to maybe learn about Alexander Pope. He was a contemporary of Newton. He was a poet and a writer and that kind of stuff. And he was poking fun at Newton in one of his little limericks that he wrote. And he said, what was the quote from Alexander Pope? I just lost it. The heavens and heaven's light lay hid in night. God said, let Newton be, and all was light. He was kind of poking fun at Newton being a stuffed up jerk. But what was it that Newton did? What's the story that everybody's been told? Oh, it's a tree and an apple. Okay. Right now, I'm not going to pull any punches. That is a lie. Okay? You have been fed a story. It is a lie. There weren't any apples. They didn't hit Newton in the head and he suddenly had some grand epiphany about what was going on. While we're at it, George Washington cut down many cherry trees, and he probably lied about that too. Okay? You guys know that story? George Washington, I cut down cherry trees, I cannot tell a lie. He's a politician. Of course he told lies. We have no historical evidence that George Washington, A, did or did not cut down cherry trees. He had a cherry orchard, so it's very likely he did both. But we also have no evidence that Newton was hit on the head with an apple, although being hit in the head would explain a lot of what Newton did. It's really weird stuff. Why are apples associated with Newton, and why is this such a big deal? The closest we can come is a journal entry that was made by a friend of Newton. This is like 20 years after the whole gravity thing. Newton's very famous, blah, blah, blah. And the friend is over having afternoon tea with Newton and asking Newton, like, how did you come up with these ideas, right? And Newton told him that as a younger man, walking from like the house that he was sleeping in to the like barn area where he would study, and he had a portion of a different house that was sort of set aside for his work. As he walked from where he lived to where he did his theoretical stuff, he would walk past the apple trees, and he would wonder at the force unseen that could pluck the apples from the trees and cause them to fall, right? So that's like the closest we can get to this idea. And we don't know how it turned and morphed into this hit in the head with an apple, right? Blah, blah, blah. So Newton is wondering about this force. The Greeks would describe this, okay, with the four sort of, what are the four elements? Does anybody remember this? Do we teach this stuff anymore? It was air, water, fire, and earth was the last one, right? Okay. So why did the keys fall? According to the ancient philosophers. What's the ground made of? Earth. And what are the keys mostly made of? Earth, like metals that come from the earth, right? And so earth wants to be near earth. Why do feathers fall slower? Well, it's got earth parts in it, but it's also must have a lot of air parts in it because it wants to be with the air. If you step back a little bit, this is actually a pretty good system, right? You can explain a lot of stuff, right? Right? It's kind of simple, right? Okay, back to the good old days. We could all wear togas. It'd be great. So you have these different concepts and ideas for why this is working. What Newton did, okay, is in the title of this slide. There's a very special word on this slide. What is it? Universal. Before Newton, we as a species had no idea just how big gravity could be. In Newton's time, they barely knew about the solar system. It was kind of this idea that was coming into its own, that Earth is not the center of the solar system, that maybe the sun, like all of these things are happening. They certainly didn't know about galaxies and other parts of the universe. That would come much later. As a matter of fact, in the early 1900s. So what Newton did is he tied the earth and the heavens together. The same force which can cause an apple to fall from a tree is the force that keeps the moon in orbit around the earth and keeps the earth in orbit around the sun. This was the first scientific idea that took us away from sort of the surface of our planet and extended it to this idea that this force is universal in its scope. Now, this was borderline like witchcraft kind of stuff, right? Like, how is it that, forces happen because things are touching each other, right? I pull on a string, I do all this kind of stuff. Forces need to, only happen between things that touch or are somehow physically attached to each other. Now Newton's coming along and saying, well, they don't need to be physically attached to each other anymore. That's incredible. And to us, it's kind of like, well, duh. What, you ever heard of Wi-Fi, man? Like, like we're used to this concept and idea of not having to see the thing that connects things together, right? But in Newton's time, this is the first time as a species that we're actually sort of exposed to this idea that forces can be exerted between things that don't, like, seemingly aren't physically connected, right, with a string. And that force, the force that lets me play a game of catch, is the same force that holds the moon in orbit or puts the International Space Station in orbit or keeps our sun in orbit around the galactic center. It's an astounding assertion to make. And for the past 400 years, it's turned out to be true. It's turned out to be right. We can get places in this solar system pretty darned easily now. So this force, right? The force of gravity between two objects, okay? Now, Newton and others would collaborate on this final form. This isn't exactly where Newton started, but we'll give you the last, most modern sort of interpretation of this, okay? Now, let me back up. I shouldn't write an equal sign yet, okay? We have a different symbol in math to explain how things are proportional to each other. Maybe not equal, but at least we can get some information about the proportionalities. Like, for example, the force of gravity can only exist between two objects that have mass. You'll learn later in 4C that what I'm telling you is a slight lie, but you'll get to 4C and figure that out. Einstein has to weigh in, and he doesn't come along till later. So if you have no mass, no gravity, which is pretty cool because, I mean, just pretty much everything has mass. So if you have more mass, let's say, for example, we're thinking about the force of gravity on us, right? Which we have another name for. The force of gravity on us is called weight, right? So how could your weight increase? Right? Can increase my mass, right? I'm not fat, I'm just expanding to keep up with the universe, right? So we can increase our mass. It's kind of hard to increase the Earth's mass, but if, let's say, the Earth's mass suddenly doubled, right? Then gravitational force would be bigger, right? It stands to reason that the force of gravity acting on objects is proportional to their masses, right? And as Newton discovered, the product of their masses. But there's another piece to it, and that is a distance, okay? And this would be the center of mass to center of mass distance between the two objects. So what happens if if I have two masses and they're, I don't know, this far apart, right? And then I double the distance between the masses. Does the force go up or down? Goes down. The further away you get from a massive object, the less the force of gravity can influence you. As a matter of fact, we talk about escaping from the gravitational influence of the sun or a planetary body when we're launching spacecraft. So if we get the distance bigger, this force will go down, right? But notice, it goes as the inverse square of the distance. So if I double this distance, right? If my distance goes from, say, r, whatever that is, right? And I make it 2r, then this force, this proportionality, right? I'd have 2r down here in my denominator, and I'd have to square that whole distance. Well, how much does it change by? Exactly how much? Not just a lot. 4 times. Where'd the 4 come from? Yeah, this becomes 4r squared, and that's 1/4 of the original thing that I started with, right? My original amount of force was right there, so it went down by 4. So what happens if I triple the distance? It doesn't go down by 3, it goes down by 9, doesn't it? And if I quadruple or 4 times the distance, that goes down by a 16th. This is called an inverse square law. And this is a fundamental feature of the universe that you and I live in. Our universe loves inverse squares. It does it for gravity. It does it for electricity. It does it for magnetism. Inverse squares are found in power laws, in intensity calculations. The sound of my voice. For those people back there in the nosebleed section, how you doing back there? Keeping each other awake? Love you guys. Right? The people sitting here, poor Michael, 1 meter away from me, right? Okay, getting his eardrums blasted out, right? Because if you are 4 meters away from me at the back of the room, then how much quieter is my voice? If the intensity of sound goes by an inverse square, and you're 4 times further away, then the intensity is going down by how much? 16 times, right? I'm 16 times quieter back there than I am up here. You guys want to switch? No? Okay. So it's this inverse square idea is built into the fabric of our space-time and the laws that we have discovered, the relationships that we've seen. And boy, 13 chapters later, we're finally there. Okay. Is a kilogram squared divided by a meter squared a Newton? No, what's a Newton? It's a MA, so it's a kilogram times an acceleration, which is a meter per second squared, right? And so a kilogram squared divided by a meter squared is definitely not a force. It's not newtons, right? Which is why this proportionality symbol, this fishy symbol, is there, right? I'm not saying these are equal to each other. I'm just saying that, we got direct proportionality between the mass and inverse proportionality between the force and the distance. So what am I going to need? What am I going to have to do if I want to write an equal sign here? You notice I was a little bit clever and left the space. If gravity depends on mass and distance, but mass and distance together don't combine to make a force, how do you fix that? Well, you're not thinking like a physicist. Invent something. Yes, right? Okay, think like a physicist. You're going to invent something, okay, right? And we're going to invent, in this case, a constant, something that we can drop in that's going to do 2 things for us, okay? Number 1, it's going to fix our units, okay? Number 2, we're going to hope beyond hope that it's actually constant, meaning that the number that we are going to figure out that goes in front of this thing isn't going to change. Whether we're on the surface of planet Earth, or we're on the moon, or we're near Saturn, or anywhere else, right? We want this number to be independent of where we are in a true universal constant. So we need a name. We need a symbol for this constant. Does anybody have any ideas? We are talking about gravity. G, right? The only problem is we've already used G, right? It's been everywhere, right? MG has just been it has stalked you through this class, right? It crops up everywhere, right? So we can't use little g. What is little g? It's a number, right? It's just, instead of having to write 9.8 meters per second squared all the time, we can just write little g and move on with our lives, okay? It's a shortcut. It's just a symbol switch, okay? And we defined it, but as you're about to see, it's not constant at all. So we need a different g. Let's see. We're going to go with big G, because physicists are nothing if not boring and unimaginative. Okay, so now supposedly we can put an equal sign here, okay, and say, okay, well, we've got an idea for what the magnitude of the force of gravity is. But what does that mean little g, like unit-wise, has to be? If this is a kilogram squared divided by a meter squared, and I need this to turn into a kilogram meters per second squared, what do the units of g have to be? So we need a meter on the top, don't we? To be able to cancel. No, we need a meters cubed, don't we? Because we want to cancel both of the meters squared on the bottom. And then we need only 1 kilogram, so we're going to put a kilogram on the bottom. And then we're going to put in a second squared. If I multiply all that together, what do I get? It's like I get a kilogram meter per second squared. Is that a Newton? Okay, so we know the units are going to be this, a meter cubed kilogram per second squared, which is just bonkers, right? But that's what it is, okay? And then we go, and Newton didn't do this, but others did, Henry Cavendish and others, went out and measured big G. And they did discover that it was a constant. It didn't matter if you were in London or Paris or Moscow, and later when we went to the moon, other places, we discovered it was truly like the same number everywhere, okay? This is what they measured. 6.673, which is not amazing at all, times 10 to the minus 11. Oops, I did the wrong unit. Usually we express this as Newton's meter squared per kilogram squared, okay? So that everything works out. What kind of number is big G? It's a really small number. This is like one of the best oxymorons I think I've ever seen. You guys know what an oxymoron is? It's a fancy word for when you put two words together that mean the opposite thing. So like jumbo shrimp. What does the word jumbo mean? Big. What does the word shrimp mean? That's an oxymoron, right? Government efficiency. Right? Like that's an oxymoron. So big G. It's not big at all, right? It's a really tiny number. In fact, it's 10 to the minus 11. 10 to the minus 11. That's like 10 to the minus 9 is down at the nano scale, right? We got milli, we got micro, and then we have nano, 1 billion. This is like almost a trillion. It's like we might as well just ignore this, right? Like it's small enough we could ignore it, right? You tell that the next time your body that the next time you wake up. Right? There's days where you wake up and you're like, oh my gosh, gravity is so much stronger today. Or I wake up and go, okay, you know what? Today, can we just do gravity this way? Because gravity always pulls which way? Not down. In. Right? Okay? Because down is a matter of pick a coordinate system, right? But in is always towards the center. So gravity acts always towards the center. Notice I didn't put a direction on that force. This is the magnitude of gravity, right? If I really wanted to write this the true way, the big physicsy way, I would write G m1 m2 over r squared negative r hat. But I haven't taught you about r hat yet. You'll learn about r hat in physics 4b. Okay? But r hat, positive r hat, is a direction that means out, away from the center. A negative r hat means what? If positive r, like along a radius outwards, what would negative r be? Inwards or towards the center, right? So that's actually how you would write it down if you were attaching all of its vector directions. But it's easier to just say, okay, if I got two masses, what's going to happen to them if they feel force of gravity? What's gravity going to do to them? It's just going to pull them together, right? Gravity is an attractive force. Gravity never pushes things away. Gravity only pulls things together, which is another way of thinking about negative r hat. So little g is really tiny, right? I don't have to worry about it at all. Little g is not going to get into my way. Anybody that's tripped, okay, knows exactly how strong. Why is gravity so strong? Why is it so hard to wake up, and why is it so bad when you trip? Get to blame the Earth again, don't we? Right? Okay. Because Earth's mass is really big. If we want to talk about the force between you and the Earth, it's your mass. Mr. Balogh's mass is around 70, 75 kilograms. Depends on which holiday we are near. And the Earth's mass, 5.98. Again, starts off with just numbers, which are boring. Times 10, now here comes the exciting number, to the 24th kilograms. Don't bother trying to conceive of this number. Your brain has trouble with anything that's bigger than 1,000. You can kind of judge millions. After that, you have no concept. Like our brains just lose the concept. You're like, I know what $1 billion. No, you don't. Okay. 10 to the 24 is a trillion kilograms. I have trouble counting. I go one, too many lots. Like that, right? Okay. But to get up to a trillion, my brain just fuses. It doesn't compute. It's just really, really big, right? So if we take a little tiny number like 10 to the minus 11 and then multiply it by 10 to the 24, are we going to get a big number out? Yes, okay? But we got to factor in distance. So what is the distance between you and the Earth? Careful. It's center of mass to center of mass. So where's the center of mass of the Earth? It's down there somewhere, right? Okay. The radius of the Earth, if we assume the Earth is a sphere, and it's not, the radius of the Earth is 6.37 times 10 to the 6 meters, or 6,370 kilometers. So, like, kind of roughly a distance from us to Europe, but in a straight line down to the center. So, gravity can be strong, but gravity can also be weak. Like it all depends on the masses and how far apart they are. So as an example, I really shouldn't, admit things like this in public, but I'm attracted to this table. This table and I have been through a lot together this semester. This is our first time together, but this table has held me up. It's been there for me. Now, what do I mean I'm attracted to this table? Is there a gravitational attraction between me and the table? Does it have mass? Do I have mass? Be careful. Yes, I have mass. Okay. Is there a distance between us? Yes. And as I get that distance closer, what happens to the force of gravity? It goes up. If I get further away, it goes down. Why am I not sucked into the table? Then what? Gravity's weaker than? No? What other forces? No. Strong, they're too small. There's another force, the elephant in the room, that just completely obliterates the gravitational attraction between me and the table. The gravitational attraction between me and the Earth. Right? Okay? Like, This force exists, but it's down on like the nanonewton scale, right? It's really, really tiny. And if the table and I were alone in the universe, we eventually, right, would get pulled together. But the Earth's gravitational field, the pattern of forces around our planet, is so much stronger than the force of attraction between other objects, right? I will not be held responsible if you try to use that as a pickup line, okay? Hey, man, we're gravitationally attracted, right? It doesn't work out well, I promise you. Okay, so there's something else. So we've talked about it already today. Your weight is mg, right? Okay. What else is your weight on the screen? It's that right there, isn't it? The force of gravity acting on an object is the object's weight. Up to this point, we always used mg, which came from Newton's second law, right? So let's be bold. Let's find out what happens if we set these two things equal to each other. Are these the same thing? Is mg your weight? Is the force of gravity between you and the Earth your weight? Yes, okay? So in this case, the mass, your mass, times the acceleration you would have if we dropped you in a no air resistance, right? Is equal to big G times your mass times the mass. What would mass 2 be? Yeah, that would be Earth's mass, wouldn't it? So let's go in there and fix that. Earth's mass, right? Okay. What would the distance be? The radius of the Earth. Okay. Right? What cancels? What's M1? You. You don't matter. Wait, no, you do. You matter. You're important. Okay? But for this result, it doesn't matter what the object is. And what we get is what? What's little g? It's big G times mass of Earth, big M, divided by radius of Earth square. Uh-oh, Raggy. What's the problem? I've done nothing mathematically or physically wrong. But what's the problem? What? It only works on Earth? What happens if I put the mass of the moon in there and I put the radius of the moon? Will I get little g for the moon? What happens if I put, I don't know, the mass of Europa, one of Jupiter's moons, right? And the radius of your... So I can get little g anywhere in the universe, right? And spoiler alert, little g is different depending on where you go, right? I taught you this already, right? Little g is different on the moon, right? Because your weight is different on the... Why is your weight different on the moon? Why is there less gravity? Because the mass of the moon is smaller, right? It's not because little g just changes and that's why. No, it's because there's less mass. And if there's less mass, there's less force of gravity. If there's less force of gravity, there's less weight on you. Yes, and objects accelerate differently when there's less of the force that's causing them to accelerate to happen, right? But even like more disturbing or mind-bending or inducing, what does little g depend on? The distance. So if I go to top of Mount Everest, have I increased the distance between me and the center of the Earth? Huh? What happens to little g on the top of Mount Everest? It's lower than it is at sea level? What happens if I go to the International Space Station? What is little g on the International Space Station? Small? A lot small? How small? What's like kind of a feature, say, of when you are seeing astronauts on the International Space Station? Something that kind of, I don't know, stands out and seems a little bit different. Zero gravity. Okay, spoiler alert, that's wrong. Okay, talk about why that's wrong in a bit. But they certainly don't seem to be attached to anything, right? Unlike us normal human beings who are firmly attached to the ground, astronauts seem to be in a state where gravity isn't pulling them to the floor of the International Space Station. In fact, it is often called, what astronauts doing stuff? What do they call that state that they're in? Zero G, weightlessness, or a weightless environment. I'm here to tell you those are all lies and wrong because of something that we are about to calculate. Let's calculate little g at the altitude of the International Space Station. Okay? We're going to calculate little g for this orbital altitude. We say 375 kilometers. It's between like, it goes down to 375, but it goes up to like 450. It kind of depends what's going on. But we are going to calculate little g on the International Space Station. And by all rights, it looks like it's pretty small, right? So it's going to be big G times the mass. Okay, what's the mass? What's the thing that is pulling on the astronauts in the International Space Station, all that kind of stuff? It would be Earth, right? The object that's doing it is Earth, right? The International Space Station is not in orbit around Venus, right? Like it's in orbit around the Earth. So the mass of the Earth is very definitely involved. Now, what distance would we put in? It's the radius of the Earth plus the altitude of the International. Okay, so one thing people don't seem to like catch on to, and I want to just point it out. By the way, that's supposed to be Earth. That's not going. Okay, so you can tell it's Earth because it's blue and green. Okay, right? So the radius of the Earth, right? And then there is the altitude that something is above the surface of the Earth. Altitude always refers to the surface distance between the surface and where you're at, okay? So you want to be careful. If they're giving you the altitude of something, that's from the surface of the planetary body that it's around, right? So the International Space Station, which always to me looks like a TIE fighter, is at an altitude 300. So that means that for the distance here, we know the radius of the Earth, right? 6.37 times 10 to the 6 meters. What do we have to do? We have to add, not the, well, yeah, the distance, the altitude, right, to that. And then we have to square that. Okay, so what does our calculate? It looks like 6.67 times 10 to the minus 11. Again, put everything in standard units. Otherwise, the units are going to drive you nuts. Okay? Mass of the Earth, 5.98 times 10 to the 24 kilograms. All divided by, okay, down here we got to be careful. We gave the radius of the Earth in meters. I gave it to you in meters right here. A lot of times it's given in kilometers. So I just want to do an example, right? Where they would say 6,370 kilometers. What does kilo mean? 1,000. It means times 10 to the 3. So 6,370 times 10 to the 3 is exactly the same as 6.37 times 10 to the 6, right? If you need to convert from kilometers to meters really quick, just write the kilometers number out and then just write 10 to the times 10 to the 3 on it, and you'll be in meters, okay? So this 375 kilometers, how do I write it down? Not just 375, but kilo means 10 to the 3. No, I wrote 6,370, not 6.37. Yeah, okay. So what would I write down for the 375? Not just 375, it's times 10 to the 3. Why do I have to write the 10 to the 3? Because it gave it to me in kilometers, right? And kilo means times 10 to the 3. So now both of these numbers down here in the denominator are in meters, which is where I need them to be, okay? So now, don't forget to square all of that. Always forget my square. Always forget my square. It just drives me nuts, okay? All right. Anybody have this number? Anybody do this on their calculator? Nobody's going to check me? All right, I'll just tell you. And you're just going to have to believe me, right? We expected it to be really small, right? Because they're not falling up there. The answer is 8.77 meters per second squared. Are the astronauts falling? I mean, the math says that they're falling, right? That's only 1 meter per second squared less than it is on the surface of the Earth, right? In fact, how far away from the Earth would you have to get for little g to be 0? Put your math brains on. How big does the r squared have to be in the denominator for the thing over there to become 0? Infinitely far away. How far is infinitely far away? Really? What does that mean? I've noticed human beings are afraid of two numbers, 0 and infinity, okay? You ask people to count backwards from 10, they will often skip 0. They'll count backwards 3, 2, 1, and then go -1, -2, -3. They'll like skip 0. You guys are in STEM fields, you're used to 0 by now. But the general public tends to have what we call a fear of 0. Maybe it's existential. They fear the nothingness or something. But infinity is the other, like, ooby-gooby number, right? Oh, what does that mean? Far away. Infinity is closer than you think. Because right now, I am infinitely far away from this table, gravitationally speaking. And why am I infinitely far away from this table? Am I being influenced in any way by this table? No, it's not gravitationally. I mean, it is gravitationally pulling on me down to the nano, right? But there's so many other things going on that it might as well be 0. So I can say, I'm infinitely far away. Am I infinitely far away from the Earth? No, I'm very much being influenced by the Earth. But let's say I get close to the moon. Now who's in charge? The moon. And am I infinitely far away from the Earth? In a manner of speaking, I am. The moon's gravity, when it becomes much more significant than the Earth's gravity, then the Earth might as well not be there. So infinity is closer than you think. Okay, but we still have to solve a problem because people refer to where the astronauts are as being weightless. Are they weightless? No. Little g is that number, and it's smaller than it would be on the surface of the Earth, but it's not gone, and it's still pretty significant. And if we think about it a different way, what is weight? The force of gravity acting on an object. Is gravity from the Earth acting on the astronauts in the International Space Station and everything that's up there? Yes. How do you know? Because it's orbiting the Earth. What's an orbit? It's a circle, right? So circles are what kind of motion? Acceleration or no acceleration? Accelerated motion. We learned about that, right? In fact, the force that points towards the center of a circle that causes the circular motion to happen, we call a centripetal force, the center-seeking force. We talked all about this. In this example, what is the centripetal force? Gravity, right? Centripetal force isn't a new force. It's just another name for a force that's already there. And so if gravity were not holding on to the International Space Station, astronauts and all their food and their poop and everything else that's up there, what would happen? If there's no centripetal force, what would the path be? A straight line, because of Newton's first law, right? So, we know the astronauts are being tugged on by gravity. We know that little g is not 0 up there. So what the heck is going on? How many forces are acting on the International Space Station as it orbits the planet? Ignore all the other planets, no sun, no moon, nothing else. Because those forces are really tiny compared to the Earth. And how do I know the Earth is winning? Because it's in orbit around the Earth, right? So, name the objects that are pulling or pushing on the International Space Station. Earth. There's nothing else. There's no other objects that are pushing or pulling on the International Space Station's orbit around the Earth. So, if gravity is the only force that's pulling on the International Space Station, then what is the International Space Station doing? It's in free fall. And the astronauts? They're in free fall too. And if everything's falling, how much normal force do you need to hold them up? None. Class dismissed. We're all done. Just leave you there. No. Duck. Everybody duck. How does it stay up? Science. Not magic. Are they in free fall? Have I convinced you that they're in free fall? Why are they in free fall? Because gravity is the only thing that's pulling on them, right? So the reason astronauts appear to be floating or weightless, they're not weightless at all. Gravity is still very much pulling on them. So they have weight. It's just that the International Space Station doesn't need to hold them up. In fact, the correct term is they are in a state of contact forcelessness. But that doesn't sound good. Weightless sounds so much better, doesn't it? Even though it's not true. NASA realized this. They tried to fix this like in the 60s. And they start calling it microgravity. That's no better. Because gravity is not micro up there, right? But that's kind of where we're stuck. We never got to contact forcelessness. Okay, so they're in free fall. They are falling. Why are they not getting any closer to the surface of the Earth? Well, they're falling down, but they are moving sideways. Thank you. What's an orbit? It's falling towards a planet, the Earth, a body. It's falling towards the Earth, but not getting any closer. That's what an orbit is. How do you pull that off? I mean, this is kind of like saying, I'm going to teach you how to fly, right? I'm going to teach you everything you need to know about flying. Everything you need to know about flying is throw yourself at the ground and miss. Douglas Adams, Hitchhiker's Guide to the Galaxy. Okay? That's a true statement, isn't it? Flying is throwing yourself at the ground and missing. Okay? The engineering that gets into that can get a little complicated, but as far as physicists are concerned, we've solved the problem, right? But how does something fall towards the earth without getting any closer? This is where all the flat earthers are going to get really mad. What is the earth doing underneath the International Space Station? It's curving away. So, let's say it takes 1 second to fall 1 meter toward the earth. What do you have to make sure to do? Move sideways fast enough so that your 1 meter of fall is equivalent to the earth curving away from you by 1 meter. If you pull that off, then you're in orbit. Insert corny old animation here.
Newton's argument was to imagine someone casting a projectile horizontally, firing a cannon, for example, from somewhere high above the Earth's surface.
No good.
From Galileo's discovery, Newton already knew that a body dropped from 16 feet above the Earth's surface reaches the ground in 1 second.
No, fail.
The distance a cannonball travels depends on its velocity. If the projectile leaves the barrel at 30 feet per second, it travels 30 feet before it hits the ground 1 second later. But Newton realized that if the projectile were fired fast enough, it would take more than 1 second to reach the ground. The Earth would curve away before the cannonball reached it. He could imagine a cannonball moving so fast it would never strike the ground. It would just keep falling forever, while the Earth forever curved away beneath it. In other words, it would be in orbit.
That guy better duck. So what's in orbit? Falling towards the Earth, but never getting any closer. How do you do one? Go fast. Which way? Sideways. When rockets, if you ever get a chance to go watch a rocket launch, you really should. They are amazing events, okay? I've been to several, but the one I remember the most was my master's work on the top of a controlled explosion going to space. The rockets, when they take, it's really hard to see in pictures or like in video or anything like that, but when you're sitting there watching it, the rocket will take off kind of almost straight up, and then it gets like, 300-400 feet above the launch tower, it will then tip over. And depending on the kind of orbit they're trying to get it into, excuse me, don't breathe and swallow at the same time. In the case of my satellite that needed to get into a polar orbit, it went up and it went, right? And we're like, oh, it's dead, it's gonna die, it's broken. No, they were like, no, they actually told us ahead of time. When it falls over, it's okay, that's normal. But the space shuttle, Starship, the Falcon launches, they tend to go up and then they'll tip over and kind of go, right, sideways like that. And you need to go up. You need to get out of the atmosphere because friction's a drag and all that kind of stuff. But mostly you need to get moving sideways, right? Most of the energy is spent getting the rocket to go sideways so that when it finally gets to the altitude you want it to be at, it's moving fast enough sideways so that the Earth curves away beneath it. Okay, I do need to pause the recording here because YouTube is going to give me a copyright strike if I don't.